Aloha, my OChem 1. I am so excited. I think this is our last video for Unit 3. This is our continuation of our SN1 E1 series. So we had a number 1 video that I hope you watched already. This is our continuing number 2 video. So I'm actually going to scroll down a little bit. And I want to do a little bit sassier versions of some E1 and SN1. So I want to just do a nice little refresh. What if we've got a nice situation like this, and we've got a good leaving group? Okay, awesome. Let's put something fun like methanol as our solvent. Now, let's stop and ask the question, what kind of reaction is this and what kind of products are we going to get? All right, let's find our leaving group. That means that this is our electrophile carbon, and it is tertiary. And then, almost just as important, look at our arrow. We only have one thing. So that means our nucleophile and our solvent are the same thing. And in fact, they're nice and neutral. And our methanol, if we draw out methanol, you don't have to do this, I'm just reminding you, but our methanol has nice available lone pair. Okay, so our solvent can be a nucleophile. I love it. It's just like our water in our last video. You can have alcohols be really good nucleophiles and solvents for this type of chemistry. So what does that scream out to us? This is an SN1 E1. Now, if this were an SN2 E2, what would be different? Well, you would have a separate nucleophile and solvent. Your nucleophile or base would be nice available lone pairs, so available that they're minus. They're nice and negatively charged. So this is totally different. And you would need to have a primary or secondary if you're going to have an SN2 reaction. So this is different. All right, so let's see if we can predict the product then. And let's draw the mechanism as a nice little warm-up. So what is always our first step in the ones, in the SN1 E1? Same first step. You lose your leaving group first. You have to make that very reactive carbocation or nothing would happen. That reaction just wouldn't happen. So then let's take our methanol and those available lone pairs and fill in that space. And then I'm going to go ahead and draw this out because remember, you now have a charge on that. You have just used one of the lone pair of oxygen. You've got to somehow give that back. Now again, we have a billion methanols or a Br minus floating around. Either one. For funsies, I'm going to use the Br minus here, even though I'm breaking some pKa rules to do that. I'm going to just remind you that your byproduct is HBr. So if we keep going in our mechanism, we are going to make, what are we about to make? This is our first ether plus HBr. Okay, so this is the first time we've actually made an ether. I love it. So now this is our mechanism for our SN1. What would be different for an SN2? We would take the same carbocation, but we would eliminate our beta hydrogen. And then we would end up, oh, wait, don't we have a choice in that? Okay, hang on a second. What does your gut tell you? We have two, how many different options? We have two that are the same. So we actually have only 2 options here. Which one do you think you're going to make in these reactions? Now the secret is, let me help you out. These are a little bit of an equilibrium. These are warm, these are slow reactions. This process, let me give you a vocab term and see if you can predict it, is going to be under thermodynamic control. So if we're under those types of conditions, then we are going to make the most stable alkene. So which one is that going to be? That's this one. So we'll eliminate that. So let's take our methanol. Let's eliminate here. And we are going to make then our most stable alkene right there. Okay, so that was a nice warm up. Now here is where the other shoe falls. Okay, this is where we still love our SN1 E1, but they do have one little sassy caveat. What about something like this? I'm going to use ethanol this time. And then it turns out if you actually do this reaction in the lab, it does work, only check it out. You end up making this. What? Okay, let's draw it out. We know from our conditions, we have a nucleophile and a solvent as the same thing. This time we have a secondary electrophile. This is where the fun begins, okay? So when you have a secondary electrophile, we're about to have a competition, just like we saw in SN2E2. When our reactions aren't quite as awesome, we start to compete. And here's what our competition looks like. Let's go ahead and start our mechanism. Oh, wrong pen. Okay, let's start our mechanism. And then let's talk about that competition. What's the first step? Always lose your leaving group first. All right, when you have a carbocation that is now secondary, remember our ranking. Tertiary is better than secondary, is way better than primary. So we just made an okay carbocation, not a good one. We're right smack in the middle here. But our carbocation is just vast open space. We have electrons all around it that can fill in this space. So we do something crazy here. I can't say we, this is Mother Nature, does something crazy, and it's called a rearrangement. In fact, we always rearrange to a better carbocation. So if we have, in this class, we'll keep these rules very nice. If you have a secondary, you will rearrange only if you can make something better. Now, what does a rearrangement mean? I feel that I need some space. So let's take our carbocation. And I'm going to keep our rearrangements to only 1-2 shifts. They can happen in farther space in nature, but we're going to try to keep a handle on it. So if we call our carbocation alpha, we are only looking at what's beta. Now, what can move a bond to hydrogen or a bond to carbon? So what I'm going to do is just color code. What do we have beta? We have 3 hydrogens on this side. We have a methyl, or hydrogen on this side. Now, what is a carbocation rearrangement? What is it? It's literally something next door moving over and literally filling in that space. Now, these rearrangements happen all the time because your carbocation is so reactive. That secondary carbocation, it is much faster and easier in space for electrons that are next door to just move over. So anytime we form a carbocation on a secondary carbon, a secondary carbocation, we will look for a rearrangement first before we do anything. And for fun, I'm going to go ahead and draw all of them that are possible. We've got 3 possible, so let's do that first one. What does it look like then if we just moved that hydrogen? So what if I now took this hydrogen and filled in that space? Well, you can't just strip a bond from the other carbon. What do you leave behind? You leave a carbocation over here. Okay, now that is now primary. Is that better or worse? It's worse. Cross it off. It's not going to happen. So let's move something else. All right, let's do another one. What if, and let's color code them. What if I move this methyl? It's next door. What if I fill in that space with a methyl? Let's try that one. What is that going to look like? Okay, so I had my carbocation there. I now moved a methyl over here. That means that I would have left behind a carbocation on this carbon, because that's where we took our methyl from. All right, and now what kind is that? Secondary. Did we make something better? No, even Steven. Okay, so then lastly, let's move this hydrogen and fill in that space. And what did we just make there? Right now we've got that hydrogen. Where is the carbocation left behind on that one? Right there. And what kind is that? Tertiary. Aha! Isn't that better? All right, you went from a secondary to tertiary. This one is going to happen. So in our mechanism then, holy crap, we're going to pause here whenever you make a secondary carbocation, and you're going to rearrange first. Just physics, just spatial. Those electrons are already there. So we are going to take that hydrogen right there and move it over. That is our carbocation rearrangement. And now we're left with our carbocation tertiary. And we have a nice hydrogen that has shifted over here. Now our mechanism looks the same. Let's take, I think, were we using ethanol? We were. Let's take our ethanol. And let's go ahead and fill in that carbocation. Okay, and now we've got our ethyl, and that is still charged. We can't shortcut that. And then something is going to take that. Let's use ethanol this time. And what did we end up making in that whole process? We just made an ether. So we just made an ether. And it rearranged. So that is our product. Okay, let's do another one of those. They're pretty fun. It's actually pretty common to have these happen in rings. Remember our ring strain? Our ring strain is actually a pretty good way to have a rearrangement happen. Let's just use water on this one. Okay. So let's see. I'm going to give the product in here, and a super secret for carbocation rearrangements, you will only use them in mechanisms, and I'll always give you the product, because at the end of the day, you can guess and predict them, but overall, Mother Nature is going to shift that in a way that works. They also need to shift in the right spatial arrangement, and we're not even going to tackle that in this class. We're just going to move stuff. So these will always pop up in a mechanism. All right, let's see if we can do this together. Let's go through our process. So let's take and let's lose our leaving group first. And then I wanted to do a ring because they're my favorite. I want to add a little step in there. And why are they my favorite? Oh my word, you guys, they happen in nature everywhere. Everywhere. We will see these again in our next unit in alkenes, and I'll show you an awesome example. You can go from shark liver oil to steroids with just a drop of acid, and they are a whole series of carbocation rearrangements. So these actually aren't just here to drive you crazy as an OChem student. They are a very natural process, and they happen in a very specific way. All right, so we just lost our leaving group, and we notice secondary carbocation. So we are going to rearrange, but only to something better. So I'm going to go through my process, and I'm marking everything that is beta and every bond that is beta. Okay, now it's getting real in here. Remember, we can move a bond to carbon or a bond to hydrogen. So for fun, I'm going to go ahead and scroll down here, and let's color code, and let's move them all and just see which one is going to work for us. So all of these are the same over here. So let's just pick one, and let's see what we make. And let's see if that's the productive one. Okay, we just made primary. Nope, not going to happen. Okay, let's try the another one. So let's take and let's move this methyl. How about right there? Okay, so if I move methyl over, what do we make? Oh, hold the phone. Doesn't that make a tertiary? Yeah. So that's in the running. Except does our product look like that? Hang on. Go up here. Double check your product. Does your product still have the 4-membered ring? No. Okay, so even though that would be in the running, that actually doesn't make our product. This is why I only give these in mechanisms. You have to form the product you're given. So let's try the sassy one. Let's use one of our ring carbons. Okay, now this is the hardest of the hard. I love it. So you know it'll be on your take home. Okay, I'm going to literally move a bond in a ring to fill in that space. Now what I like to do is draw it funny first. Okay, look, I'm leaving all of my other bonds. And what I've just done was move that bond over to here. And then where is the carbocation now? Where did you leave it behind? Right there. So now I'm going to draw it pretty. That is now a 5-membered ring. That was a little bit too fluffy. And then our methyls are here and here. And look at our carbocation. Why is my pen just going to fluffy? I guess I'm too excited. There you go. Now we can continue. Now we're talking turkey. Let's continue that in our mechanism. So we are going to choose this rearrangement. And we have a carbocation left here. Now we can continue the rest of our mechanism, fill that space in with water. Don't forget your water is still charged there. So let's use something to give that lone pair back to water. And now you have your product. Okay, I love it. I love it. I love carbocation rearrangements. They are so much fun. You have a bunch of them in your homework. You need to maybe try some of these before class on Tuesday so that we can work through them together. I love it.